Hey guys, it's Chili here. Welcome back to Advanced C++ Tutorial 2 Part 2. In the last video, we learned about translation and scaling. We set up a screen coordinate transformer that let us work in math coordinates. And we set up an entity that holds model data and position and scaling information and can poop out polylines, which are copies of the model transformed from model space into world space. Now we're going to implement sexy scrolling with a camera component that sits in our pipeline. We're going to build a drawable object that encapsulates built-up transform information together with polylines in nice renderable packets that can flow down our pipeline. And I'm going to give you guys a number of interesting coding tasks for the homework. Alright, now let's move on to something that I think you guys are going to be pretty interested in. Scrolling with a camera system. So all the games that we've been making so far, they've all been single screen games. The entire game world fits into the screen. But in real games, you're going to have very large worlds, and it's not all going to fit on the screen, so you're going to have to scroll through the worlds, basically following the action, usually following the player's character around. And let's figure out how to do that. So the general setup is you got a world, you got a bunch of things in the world, it could be sprites, tiles, 3D models, doesn't matter. But you got things in the world, and then these things are too big to all fit on the screen at once. So you've got your screen that is showing a portion of the world, and everything else is going to be outside of that. And what you want to do is you want to scroll around, you want to move your camera. We say that the position of the world that we are currently viewing, that is determined by camera. And we want to scroll that camera around so that we can view different parts of the world. So how does this work mathematically and in terms of transformations? Well, another way you can think of this, like if I scroll this camera down, how does the scene change? Well, this guy, if I scroll the camera down on the screen, in terms of what we see on the screen, it looks like this star is moving up. All the things, when we scroll down, all the things are moving up. So scrolling the camera down is synonymous to basically scrolling the entire world up. So what we really want to do when we change the camera's position, when we make it, say, larger in the Y, is we want to subtract an identical amount from all the things in the world in the Y-axis. So we want to apply a filter to everything that we draw. So now our filter chain, our pipeline is going to look like this. We've got our entity, it applies its own position and scaling to the model, poops it out, and the camera is going to apply a camera translation to that. It's going to pass that on to the coordinate transformer, which is going to do the translation and the flipping, and that's going to pass it on to graphics. So let's implement the camera. Just to get you guys up to speed, what I did here is I gave the entity, the constructor for it, able to take a position as well as the model. And here in, let's go over to game.h. I have added a vector of entities to the game, so that's going to be our scene, and then I'm going to add a bunch of stars to the scene, and then here in compose frame, I'll just draw all the stars, and if you run that, here is the current scene, and we want to scroll through this scene. Alright, so we create a class camera. What is it going to store? Well, it is going to have to store the position of the camera to be used for the translation, and we're also going to want to store a reference to the coordinate transformer that we're going to pass our stuff onto, our vertices, our polyline after we're done with it. And the camera constructor, we'll just construct it at 0, 0 to begin with, but we do need to take in that coordinate transformer, so let's do that right now, like this, and let's add a few accessors and mutators. That looks something like this: a getter, something to move it by an offset, and something to move it to a position on the screen, or in the world, I should say. All right, now we want to do the actual transformation. So again, we're just going to copy we'll copy this basic setup from coordinate transformer. And we'll paste it in here. And what are we going to do? Well, offset is equal to, all right, so this is going to be a little different. Offset is going to be equal to negative position. There we go. We don't really need to do that, do we? We don't have any kind of scaling going on yet. So we'll just do v minus and equals position. And now we don't have graphics, we have CT, so we're going to do CT draw closed polyline, and we are going to do std move, because we don't need this resource anymore, poly. So we'll move that into closed polyline, and we're not making any unnecessary copies. We're just moving it along down the chain. And that should be enough. In game.h, we add the camera like this. Don't forget to include it. And in game.cpp, we've got to initialize that camera. Like this, we pass it to CT. It gets a reference to that. And then down here, we want to draw to our camera. Nothing else should change. Good, no red lines. Now we want a means to move our camera, so we're gonna co-opt our old means for moving entity and use that to move the camera. And that'll look like this. And now the moment of truth. Does it build? It does seem to build. Now, does it work? Well, let's press the buttons and work. Ah, there we go. We are scrolling around in the world. We can explore the starry night, and it is good. All right, so that is task 1 complete. All right, the next thing I want to do is I want to add the ability for the camera to zoom in and zoom out of the scene. Now, when you zoom in on something, what happens? The thing gets bigger in the viewport, right? When you zoom out, it gets smaller. So logically, we're looking at a scaling operation. So we want to add a scaling transformation to our camera. So where did I put my camera? So let's add a float scale equal to 1.0f to our camera. And then we'll add a setter and a getter. And that will look something like this. And then we just want to go into game.cpp and enable that in here. That'll look something like this. I might name it, zoom instead of scale for a camera, but it doesn't matter. It's the same stuff, right? So there we go. One more thing that I kind of missed. We also have to actually apply the transformation. So for the entity, we apply the scale and then the position. So let's try that for the camera. That would look something like this. If we try to run it, hopefully we won't get any build errors. And here we go. We've got our stars. We can zoom in and we can zoom out of our scene like this. And we can translate. And this is weird. This is weird. It's not like we're zooming in on the center. It's like we're zooming in diagonally here. That doesn't seem correct, does it? If I move down like this and then I zoom out, I zoom in. If I zoom in, it should zoom in on this area here. This should disappear, but this doesn't disappear. We keep zooming in diagonally into this position. So what's the story? Well, basically, when the vertices come into our camera, they are still based around the world origin, which is not the same as the camera origin. So when we scale them, we're scaling them around the world origin, and that's why you get that weird effect. What we want to do is we want to translate them so that they are now going to be based around the camera origin. We want to do the translation first. Then if we scale, we're going to be scaling around the center of the camera. So watch this. So now if I move down, put this guy in the center, I'm now zooming in on the guy that I'm actually centered on, instead of zooming in on, the center of the world. So, interesting. Depending on the situation, you don't always want to scale first. Sometimes you want to translate first and then scale. You got to think about what you're doing, about the effect you want to achieve, and you then decide the order of your transformations depending on that. All right, now let's take a step back and look at all the operations that we're doing on our vertices. So we're running a bunch of loops over them, and in those loops, we're performing a bunch of operations. So first, we are scaling by the object scale, the model scaling, the entity scaling, I should say. Entity scaling, then the entity translation, then the camera translation, then the camera scaling, then the coordinate flip, and then the coordinate translation. So we're doing all these guys. But let's take a look at, for example, the translations here. So we're looping through them all, we're adding T1. We're looping through them all, we're adding T2, and then here we're looping through them all, we're adding T3. There's 3 loops, but think about it. We could also just do V1, so we could calculate T result is equal to T1 plus T2 plus T3, and then we could just do one single loop where we do V1 plus T result, V2 plus T result, etc., etc. So we could combine these 3 translations and then just run them all in a single loop where we do in a single addition to each vertex instead of 3 additions for each vertex in 3 loops. So that's a great idea, except we know that we can't change the order, the relative order of scaling and translation, because that would just mess up our scene. We're not allowed to do that. So the best we could do with that situation is maybe combine these 2 translations into a single operation. The rest of them can't really be interchanged unless we do a little thinking and we come up with a clever solution. So the reason why we can't just combine all our translations together is, well, let's take a simple example here. So let's say we have an operation that is translate into a scale into another translate. So if I've got a point, let's say I've got a square here, and I do a translation, I move it to here. It's not going to show up that well on the screen, but you get the idea. All right. Then I scale it by 2, something like this. And then if I translate it down by 2 after that, that should give me this guy right here. But what if I were to combine these 2 translations? Well, the thing is, when you do your first translation, let's see if I can find a good color. Let's just use black. When you do your first translation, you are moving all the points over by 3 and up by 2, which effectively is moving the center of the object here. Then when you scale it, you're also scaling that center point. So when you apply this scale, you're also scaling this translation as well. So you can't just take these guys, add them together and pull them out, because you are losing the fact that you scaled this first translation here. So if we want to combine all our translations together, we have to take into account the fact that scaling will scale all of the previous translations. If we do that, then we can cram all of our transforms into a single transform and apply it only once at the end. Let's try this out in code. So in order to build up the translations, let's create a new data type, and we're going to call it Drawable. So Drawable is going to store a copy of the model that is going to be drawn. So we're going to do a vector of vec2. We'll call this one the model. It's a copy of the model, but you get the idea. Then it is going to store up the built up translation part of the transformation, and it is going to store up the built up scaling part of the translation. And we're going to set this equal to 0 or 1, and we'll set this one initially equal to 0, 0. So here we have our drawable. We'll make the constructor. We'll make a function to translate the drawable, and we're going to make a function to scale the drawable. Now this one, again, you got to be careful. Scaling should also scale the existing translations that have been built up. So we go float, scale, in, and we should do scale times and equals scale in. So when you scale an existing scale, you're multiplying it. And we also want to do translation times, no, that's not times and equals scale in. And there we go. So now we can use this to build up translations by just single scalar operations. And then when we're ready to draw it, then once and only once we apply these to all the vectors in the model. So how are we going to do that? Well, I think the best way is to keep things encapsulated, to keep this data inside of Drawable. All we got to do is we'll do a void render, and we want to take a reference to graphics. And what we're going to do inside here, it's quite simple. We're going to run a loop, and inside that loop we're going to translate all the vertices of our model. And then when we're done that, we are going to, well, I guess render probably needs to take, this is kind of weird now, because we got to wonder, where do we pipe in the color? So I think the Drawable will store the color, and that color will be passed in through the constructor like this. And then after we're done transforming the vertices, we go graphics dot draw closed polyline model color. And there you go. That works. But now we've got to fix all the parts of our pipeline and our entity to use the drawable. So we'll start with coordinate transformer. We'll just give the function, we'll call it draw, and it will just take a single drawable. Take it by reference, I guess. Like that. Haven't decided yet. Obviously we need to know what a drawable is. Include drawable. And since we're not changing anything about the coordinate transformer, we can actually make this const. I've probably done that before. And then in here, we'll just calculate the offset like this. Now we want to, for the drawable, we want to apply the flip. This is interesting because the flip applies a scale, right? Multiplying by a scalar is a scaling operation, -1, but it only applies it to y, not to x. So that doesn't actually fit into our current situation. We're going to have to change things up a little bit. We're going to have to go float scale y is equal to 1 and scale x is equal to 1. And then we need to do v dot x times scale x and v dot y times scale y. This doesn't increase the amount of work done, by the way, because when you multiply a scalar by a vector, you're still doing 2 multiplies. So we're just breaking it out a little bit, separate for x and y. And here now, for scale, we can just do scale x times scale in and scale y times scale in. So this is scaling for equal for both axes, but we also want one that can scale separate. So we'll go void scale independent. And in this one, we are going to, obviously scale these guys independently. And we also have to split up the scaling on the translation because it's different now for the axes. So now we've made our drawable a little more flexible. And in here, we got to apply our scale of -1 in the y. And that's going to look like this. And then we want to apply our translation. And that's going to look like this. And then we want to render the drawable to the graphics. So we go drawable dot render GFX. And then we don't need this loop anymore, so we can get rid of that. And let's make this const just because that's my fetish. And there you go. So the coordinate transformer is now all good. Now let's do something similar for camera here. And that's going to look something like this. Make sure that you translate first and then scale, and also make sure you negate your position when you're translating. And then you call draw on drawable and you pass that guy on. Beautiful. Now I guess next thing is going to be entity, because we've got to change entity so that it poops out a drawable when we want one. So actually, the first thing I'm going to do is I'm going to make each entity store the color of the entity. And then you should be able to set that in here. And we'll just set it default to yellow. Something like that. And now we want to be able to poop out a drawable. So drawable, get drawable. And we're not going to change anything about the entity itself. So we can make that const. I imagine we're also going to have to include drawable to make everything kosher. Maybe not, maybe so. We're going to do it anyways. And now in here, how do we create a drawable? Well, we can just go drawable. We'll just say D. Well, my IntelliSense gods have failed me, but that's okay. Drawable D, and it's going to need the vector, so it's going to need the model, which is just model. Copy that in, and it's going to need the color, which is just C. So we create that. Do we need to do anything to it? I don't think we actually... we do. Of course we do. Because we need to apply, first off, the translation and the scaling of the entity itself. So to do that, we scale first. So we go d.scale by the scale. And then we do d.translate by the position. And then we return D. And copy elision is going to just make that all nice for us. So now we don't need this bozo anymore. Save that. So far, probably so good, I'm going to say. We'll see. Now we need to go to game.cpp. And we need to change some stuff up. This stuff should all be good, just this one line here. So we do camera, draw, entity.get drawable. That's not what we need. And it should be good here. This should be excellent for us. And if I build that and run it, so far so good. The translations at least are looking okay. And we can zoom in and out, and there are no weird zooming bullshits to be had. So it looks like this is actually the best thing ever. Because now we can have a whole chain. Let me just get my... So yeah, we can have a whole chain of filters here, a whole bunch of them we want, more than these. And they're all going to apply their own transformations, but we don't have to loop through all the vertices for every filter. We can just, for every filter, we can just apply a few quick adds and multiplies, build up a transformation, and then at the very end, apply it once in a loop. Now, we can actually do a little bit better than this, because... I mean, think about it. Now let's go to Drawable again. What we're doing here, do we really need to copy the model? The answer is actually no, we don't. We could just store in here a reference, a constant reference to the model. And then in render, we could apply these transformations to each vertex on the fly, and we wouldn't actually have to maintain a copy of each of our models. I'm not going to do that here, but just know that it's possible to replace this with a reference to the model, and then in render, we would just put a loop in here and draw each of the lines, transforming the vertices as we go. And that would make our drawable objects very lightweight. They would just be, a few bytes to store the whole drawable. The raw data would remain in the entity here, and it would be transformed on demand as necessary. All right, now for the homework, I want you to create this. I'm going to give you a laundry list of tasks, and you can complete them in, any order that you want, really. The list is going to be on the wiki. So what is all going on here? Well, first of all, you're going to want to generate a scene, a rather large scene of stars that have been randomly placed, and have random sizes, random shapes, meaning the number of points and the ratio of the inner and outer radius. That's all randomized. And I want you to do that, and I want you to create them. And you want to create them in a rather large area. Let me just zoom out here so I can show you. So I created them in this sort of area here. And you've got a big star field to work with. So that's step number one. Oh yeah, and you don't want any overlapping. So make sure that none of them overlap. Now step two is fairly straightforward. As you can see here, I'm not using the keyboard to scroll. I'm using click and drag. So you want to implement click and drag scrolling for your camera component. The next task relates to what I was talking about earlier, in that you want the drawable not to store a copy of the polyline. You want it to store a reference to the polyline and then convert those vertices on demand as the polyline is being transformed and rendered at the end of the pipeline. That's going to give you a nice performance boost, but there's a bigger performance boost that you can have. In the current system, if you zoom in, you've only got a few stars on screen, but the way the engine works is it will try to draw all the stars in the entire scene here, even though most of them are going to be clipped away, and it's just a big waste of resources. So what I want you to do is, let's say, you're zoomed into a small area of the screen, this area here. You only want to draw the stars that are inside this area. The rest of them you want to skip by some means. So the guy out here, that's way outside the screen region when you're zoomed in. So you want to cull that. You want to ignore it. So try to figure out how to do that. And of course, I'll show you in the solution video. And the last task, just for a little fun, is, add some animation to the stars, make them scale up and down rhythmically, and also make them pulse their color rhythmically. So those are your tasks. It's going to give you experience with all sorts of transforms, and it's going to get you more familiar with the pipeline concept. But that's going to about do it for today. This idea of transforms and pipelines is going to be encountered over and over as you learn 3D graphics, so it's well worth your while to get a good grasp on it right now. Now, the other thing I want to say is the design pattern that I've shown, the drawable, it's just an idea. It is not the way things should or must be done. Just want to get that out of the way. It's just an interesting idea throughout there. And it's very simple at this point, but it can be made more flexible with the addition of, inheritance and polymorphism with templates. You can have it so that different types of entities output different kinds of drawables, but they can all flow down the same pipeline. But again, it's just one idea. Thanks for watching. I hope you enjoyed the video. If you did, hit that like button. It helps a lot. And I will see you soon with some more advanced C++.